Chap Section 4, Chapter 2, Section 4 deals with symmetry. What does symmetry mean? I know you guys are looking in the packets. From now on, I'm going to give you two packets. One of them is just going to have the example problems themselves, nothing more. And then I'll give you this packet with all the definitions, everything later on. Because I have the students spend all the time flipping through these things looking for what we're talking about. Symmetry simply means mirror image. If something is symmetric, that means it's equal on both sides. If you look at a picture on a smooth lake, whatever's on top of that lake reflects on the bottom, that's symmetric. That's symmetry. We have three forms of symmetry. The first one is about the y-axis. We use the word about. That means that's what it reflects across the y-axis. If I had a point at that location there, what is its location? This is the y-axis, this is the x-axis. If it's symmetric about the y-axis, that means there's another point here. What is its location? So if something is symmetric about the y-axis, what changes? And how does it change? How does it change? So what changes on it? Right. The x value changes sign. That's all that happens. If you look at 2 points and everything's the same except the sign of the x value, then you know it's symmetric about the about the y-axis. About the x-axis. So here's the x-axis, here's the y-axis. If I flip this point all the way across the x-axis, what changes there? So this one is 1, 3. This one is 1, -3. What changes there? The y value changes sign. And then the third one is about the origin. Location of this one is 2, 1. If I flip it across the origin, it will go to -2, -1. So if it's symmetric about the origin, what changes? the signs of both x and y values change. That's all it changes. Not the numbers, only the sign. Let's see how we can test this. Oop. So this about the origin. The way you can look at it is it flips across the x-axis, then it flips across the y-axis. Or vice versa, reverse, the y-axis, then the x-axis. So let's look at an example here. Test y equals x squared plus 2 for symmetry with respect to this. WRT is with respect to some x-axis, y-axis, and origin. Okay, let's look at how we do this. So for the x-axis, here's the first one. X-axis. Remember, how do we know if it's symmetric about the x-axis? It changes the value of y. So y changes from positive to negative y. And we get the same value. So select a value for y. Doesn't matter what it is. Say it equals 1. If it's symmetric about the x-axis, if I plug in both of these answers, I should get the same x values. Let's see. So we have 1 equals x squared plus 2. Negative 1 equals x squared plus 2. I'm using the same the equation x squared plus 2. Solve for x. Subtract 2 from both sides. I got negative 1 equals x squared. Square root both sides. I get x is equal to plus or minus the square root of negative 1. Remember, anytime you square root something is squared, you have to put a plus or minus in front of the answer. And the other one, when I use y equals negative 1, subtract 2 from both sides, I get negative 3 equals x squared. Square root both sides, I get x equals plus or minus the square root of negative 3. Are they the same? They're not equal, so it's not symmetric about the x-axis. Again, so to check x-axis, you plug in a y and put a negative y and see if you get the same x values. B, let's see if it's symmetric about the y-axis. For the y-axis, we change x to negative x and see if we get the same values for y. So x, I'm going to use 2. I'm going to check it with -2. So y equals 2 squared plus 2. 2 squared is 4 plus 2 is 6. So it's the point 26. -2 squared plus 2. -2 squared is 4. Plus 2 is 6. So this one is -26. X values change signs, Y values stay the same. So yes, it is symmetric about the Y-axis. Because I put the same value but different signs, I got the same answer. That's symmetry. How do we test for origin? I change X to -X and Y to -Y. I should get the same answers. So X, let's say, is 2. Change it to -2. So when I change X to -X, what my answer should become, one of them should be positive, one of them should be negative, but the same value. So Y is 2 squared plus 2. Y equals -2 squared plus 2. So my X's give me. So is it symmetric about the origin? Did the X change signs? Yes. Did the Y's change signs? No. So not symmetric about the origin. If you don't want to write origin, not symmetric about 0, 0. You can write the origin that way.
So it's only symmetric if the signs change.
Yeah, so I put 2, I plug in -2. I get Y's. The only thing changed is the sign. The answer should be the same number, but different signs. Yeah, so the origin is tricky that way because you have to make sure when you finish everything, it's just the signs change. Oh, only, yeah. Example 2. X squared plus Y to the 4th equals 5. Again, is it X-axis, Y-axis, and origin? Let's try X-axis. Remember, the X-axis is vertical, so I plug in a value for Y, let's say 2, and I plug a value for negative Y, the same number but negative signs. I should come up with the same X values. We have X squared plus 2 to the 4th equals 5. X squared plus 2 or -2 to to the fourth equals 5. This is my inputs. X squared plus 2 to the fourth is 16. Subtract 16. So x squared equals negative 11. Square root both sides. So x equals plus or minus square root of negative 11. Negative 2 to the fourth power is positive 16. Negative 2 times negative 2 times negative 2 times negative 2. All the negatives cancel. 2 times 2 times 2 times 2 is 16. Subtract 16. So x squared equals negative 11. So x equals plus or minus square root of negative 11. So is this symmetric about the x-axis? Yes. And look at for the y-axis. For the y-axis, remember, what you do here is you change x to negative x. And you get the same answer. So x is equal to 2, x is equal to negative 2. Plug it into the equation. So I have 2 squared plus y to the fourth equals 5. 2 squared is 4. Y to the fourth equals 5. Subtract 4. Y to the fourth equals 1. I'm solving for y. How do I get rid of the 4? Remember, if it was a squared, I would square root both sides. But since it's a 4, I got to take the fourth root of both sides. Y is equal to plus or minus 1. And now I put negative 2 in there. Negative 2 squared is 4. Subtract 4. Y to the fourth equals 1. It's the same thing. So y is equal to plus or minus 1. So yes, symmetric about the y-axis. Since it's symmetric about both x and y, we can pretty much sure it's symmetric about the origin. So x equals 2, x equals negative 2. We just did those, and it gives us y is equal to plus or minus square root of our fourth root of negative 11. Y is equal to plus or minus the fourth root of negative 11. So yeah. Yes. So that's what you look for. Is a circle symmetric about the origin? The answer is yes and no, depending on where the circle is located. So in other words, if the circle is centered at the origin, yes. If the circle is outside the origin, it's no longer symmetric about the origin. Is this it's if it's straight up and down, if there's a center, yes, then it's symmetric about the y-axis, but not the x-axis, because x-axis is all the way down here in the origin. So be very careful if there's any transformation, any shifts, which we'll talk about in this chapter. The last topic in this section is odd versus even functions. With respect to what we talked about, odd functions are symmetric about the origin. So if a function is symmetric about the origin, then we know it's an odd function. If it's an even function, it's symmetric about the y-axis. There's nothing about the x-axis. I can go through a whole litany of examples here. Well, because we're short of time, we only have like 10 minutes left. I'll give you the shortcut. Odd functions only have odd exponents. Only odd exponents. In other words, if the equation looks like this, and so forth. X by itself, what is its power? One. It's an implied one up there. So if the equation only has x's with odd powers, it's an odd function, which means it's symmetric about the origin. We've seen that. Have we seen these equations before? Yes. This is x cubed. This is the cube root of x. Well, we've seen the third one also. Come to think of it. This one's 1 over x. And another one, the equation x. If you notice, all of these, the exponents are odd. Remember, for even, it's got to be symmetric about the y-axis. For a function to be even, have only even exponents and or are constant functions. For example, a constant function, if it passes through some value k, is that symmetric about the y-axis? By definition, yeah. It's just a mirror's image. So if it's a constant function, then it's an even function. Or if it's even. This is the function. Remember what function of this one was? That's x squared. What's this function? Absolute value. Very good. Now, why is the absolute value an even function? Because the formula for the absolute value is square root of x squared. X is squared. So is this odd or even function or neither? Since all the x's are even, it's an even function. How about this one? Why?
Because it's still even,
All of these are even. It's even exponents and constant functions are even. So this is even. How about that one? It's odd. How about this one?
even.
Because the constant can only be in even functions. This one, these are odd. This is even, so it's neither. You can't combine them. So yeah, instead of going through all that stuff, plugging numbers and see what happens, it's just easy to look at the exponents. So if you have a constant term and all the exponents are even, then it's even. Yeah, if you have a constant and any one of them are odd, is that odd, even, or neither?
Neither.
Yeah, because this is even, this is odd. It ruins it. You cannot mix and match. Looking at our example here, is A odd, even, or neither?
Different.
It's definitely odd because all the exponents are odd. How about the next one? Even, because you have even exponents and or a constant. So that's odd and that's even. All there's to it. We only have one more topic in this section, in this chapter. And that one